Here we have discussion about how Ampere's law is not consistent everywhere, as well as we are going to see about displacement current density. Earlier we have discussion about convection current as well as conduction current. So that we have seen that in case of convection current, we don't require any conductors. Okay, but in case of conduction current, we require the conductor, and here you will see that what is the necessity of the displacement current, what is use of this, and how it is going to make Ampere's law valid. Okay, so let's start with the first. We'll see how Ampere's law is not consistent. Okay, so here if you see that in case of a static EM field, we have seen that EM means electromagnetic field. So means electric field and magnetic field both are present. So you have seen already that when we have current carrying conductors, so it's going to produce the magnetic field around it. So finally we have EM field. So in the EM field we have relation del cross H equal to J. So where J is the current density, and current density is what? J equal to I by A, current per unit area. So now we have concept that divergence of the curl of any vector field is zero. So we can write here divergence of the equation 1 del dot del cross H equal to 0, and for the right side we have del dot J. So finally, from the as per the continuity equation, if you are able to remember about, we have continuity equation earlier. So there we have del dot J equal to minus dou rho B by dou T. So now here how it is possible that del dot J will be equal to 0, since charge density will not be 0 there. So finally this equation 2 and 3 give us the contradiction. So that equation 1 what we have written earlier, that is the del cross H equal to J, that must be modified. So that means some additional term must be added here. So in the equation 1, apart from the J, we have J plus D. So this JD is the displacement current density. Again, we have now divergence of the curl of any vector is 0, what we have seen earlier. So on the basis of that, del dot del cross H equal to 0. So finally, del dot J plus del dot JD should be 0. So now by using equation 3 and 5, okay. So in equation 3, what we have seen, del dot J cannot be equal to 0. So finally, in this situation, it cannot be 0. So finally, by using equation 3 and 5, we are able to write here del dot JD equal to minus del dot J. Okay. So here we have expression about del dot J, that is the dou rho B by dou T. And already we have earlier by the Maxwell equation also we have seen del dot D equal to rho B. Okay. So that value we are going to substitute here. What was the expression earlier we have? Del dot D equal to rho B. So now finally, once we substitute in place of rho V, so finally that rho V is what? Del dot D. So this rho V is replaced by here del dot D. So del is taken outside. So finally here del dot JD equal to del dot dou D by dou T. So from here, if you liquid that, we'll get the displacement current density equal to dou D by dou T. So this is the displacement current density. So finally, now this equation 1, what we can write, del cross H equal to J plus JD, and we can write J is what? Sigma E plus JD is what now? Dou D by dou T. So now this is the final expression for the del cross H. So now we have conduction as well as displacement current density both. So now here, if you are going to see that when propagation of the electromagnetic waves takes place, then it is possible due to the displacement current density. So displacement current density is going to play the major role when wave is going to propagate. So in the case of low frequency, that JD, that means displacement current density value is less. So that can be neglected in compared to conduction current density. But in case of higher frequencies, like in case of radio, television, this both having significant value. So we can't neglect. So finally, displacement current is given as, so already we have seen that I equal to integral of J dot ds. So on the basis of that, displacement current is the integral of JD dot ds, and JD value is what? Dou D by dou T. So this is the expression how we are able to find the displacement current. So now here we are going to consider two different situations. So in this, we are seeing that this wire having current, okay, from the top to bottom direction. And here we have capacitor. And this line carrying current is being enclosed by the another path, like you have earlier Ampere's path. So now when this is the, like you can say that we can keep some disc-like structure also. So that surface area is what here? S1. So this is the disc-like structure. In between, this wire is going to pass. So that surface area is S1 here, and this is the closed path also, okay, that line. And finally, another side here, if you see that we have like a structure of the balloons. So only that surface of that balloon is going to pass between the capacitor. So that curved surface area is denoted here by S2. And again here, this disc upper portion, like you can consider also as the hemisphere. So this upper part is the circular, okay, and current value is same. So now in the both situation, now here we are going to see that how we have different values, okay. So now here in the first situation, okay, due to this displacement current is the due to time varying field that we know from the starting onwards. And now current through the capacitor when we are going to obtain when alternating voltage source is applied to its plates. So now from the Ampere's law, we have integral of this field intensity S dot dl over the closed path is equal to current enclosed. So finally here current enclosed is what? I. And this current is given as integral of J dot ds, okay, over the surface S1. So now we can use another is the structure that is the balloon shaped surface S2. It is going to pass between the capacitors. So in this situation, what you are seeing that current enclosed is what? 0. So that current carrying wire is not enclosed by this Amperian path, by the surface of that balloon. Okay, only it is going to pass between the capacitor. So that means here conduction current is 0. So no conduction current is going to flow through the surface S2. So equation 9 and 10 again is going to create the conflict. In the one situation, you are getting that integral of S dot dl is I. Another situation, we are getting integral of S dot dl equal to 0. So it shows that inconsistency of the Ampere's law. So finally, displacement current is included in the Ampere's law. Okay, so total current density, we have J plus JD. So now if you are going to write JD equal to 0, then equation 9 also is going to be valid, since when wave is going to propagate, this displacement current density is going to play the major role. Only at case of low frequency, we can neglect all those things. Okay. So now finally here, if you see that in this, if you are going to put J equal to 0 in equation 10, so then we have expression. This JD is due to the displacement current density. So that JD dot ds, again, we have seen already JD is what? What is the value of the JD? JD is written as dou D, okay, dou D by dou T. So that is being replaced here, and D dot ds, okay. So we have from the earlier by the Gauss laws, flux is the integral of D dot ds, and this total flux is what? It is the charge enclosed. So finally integral of D dot ds is going to give us the value here. So from here, this we are going to get the total charge enclosed, that is the Q. So it's going to become dq by dt. And rate of flow of the charge is what? Current. So that is equal to I. So it gives same current in both cases. Okay. So conduction current in S1 and displacement current in the situation of S2. Now we are going to summarize here about Maxwell equations and other equations what we have seen earlier. So that Maxwell equation here in the time varying field, we have in the differential form as well as in the integral form. So in case of differential form, we have del dot D equal to rho V. And finally, in the differential integral form, we have d dot ds integral over the closed surface equal to volume integral of rho V into dV. So this equation we have from the Gauss law. And we have del dot B equal to 0 and integral of B dot ds equal to 0. So it shows that non-existence of isolated magnetic charge, and del cross E equal to minus dou B by dou T. And in the integral form, it is the integral over the closed path E dot dl equal to minus dou by dou T, integration over the surface B dot ds. So this is coming from the Faraday's law. And just now we have seen del cross H equal to J plus dou D by dou T. So finally here, integral form, integral of H dot dl over the closed path equal to surface integral of J plus dou D by dou T. Okay, so this is coming from the Ampere circuit law. And we have Lorentz force equation, that is F equal to QE plus inside the bracket E and U cross B. So U is the velocity. And we have earlier discussion about continuity equation. So that is del dot J equal to minus dou rho B by dou T. So apart from the Maxwell equation, these are the also important equation. And here we have D equal to. So this D generally, what we write here, D equal to epsilon E. Okay. So finally, this P is here for the polarization and B is the mu H. Okay. And again, if mutual inductance takes place, so we have mu naught inside the bracket H plus M, and current density J equal to sigma E plus rho B into U. And these are the different boundary conditions. So in the different situation. So now if you see in case of electrostatics, what we have seen, again in the magnetostatics, what we have seen. So all boundary conditions are summarized here. So here tangential components are equal. Here we have seen that tangential component will be equal in the magnetic boundary condition if K is going to be 0, and normal components of the flux density in the electrostatics, that difference is rho V. And here in case of magnetic boundary condition, normal component of the flux density is conservative. Okay, so An is used for the normal unit vector. And in case of perfect conductor, so sigma is infinity. So electric field, magnetic field, and this J is 0, and Bn also will be 0, so it will be equal to mu H, and tangential component is going to be 0 in this case. So these are the major discussion here in case of electrostatics and all this we are trying to summarize here. And some more equations here we have B equal to mu h, D is the epsilon E, and in case of equilibrium, we have del dot D equal to rho B and del cross H equal to J plus dou D by dou T. So these are the discussions. Okay. So any doubt is there, please write in the comment. Thank you. Thank you very